Welcome to Chapter 10, Current Security Issues in the Digital World. I am Dr. Jabbar Al-Maliki, and this is our University Utara Malaysia lecture on modern network architecture. For decades, cybersecurity was modeled after a physical vault, relying on a single heavy perimeter to secure data. As networks expand, this central perimeter becomes porous and eventually fails to contain the internal pressure of modern data traffic. As undergraduate computer science students, you are entering an industry where the traditional walled garden approach to security is technically obsolete. This is a legacy closed network. It operates as a self-contained system behind one fortified outer boundary. Cloud computing, artificial intelligence, and the Internet of Things bypass that boundary. The system mutates into a complex web of interconnected nodes, reaching far beyond direct physical control. This distributed architecture allows organizations to scale operations globally, processing immense datasets across continents in milliseconds. However, every new connection required to achieve that scale creates a new pathway for intrusion. We define the total sum of these exposed pathways as the attack surface. It is a metric of every single point where an unauthorized user could enter the architecture or extract data. Today, we will deconstruct these modern architectures. We will trace exactly how distributed technologies fail under pressure and examine the resulting technical and ethical consequences. Cybersecurity has evolved into a discipline of continuous vulnerability management across the entire ecosystem. The first major layer of this architectural expansion is cloud storage. Storing massive databases in third-party environments like AWS or Azure means organizations surrender direct physical access to the hardware hosting their data. In this cloud bucket configuration, the primary vulnerability is human error. An engineer accidentally toggles an access control list from private to public. This acts as an open door, instantly accepting unauthorized connections and allowing external nodes to siphon out proprietary data. This exact mechanism of engineering oversight is the direct cause behind severe, large-scale data leaks across enterprise networks. In centralized cloud architectures, a single keystroke error by an administrator generates exponentially more risk than advanced technical exploits. The Internet of Things, or IoT, expands the attack surface further into the physical environment. Smart devices like industrial sensors or office thermostats are built under tight engineering constraints. They have limited hardware memory and rarely receive ongoing firmware patches to fix new vulnerabilities. These unpatched devices are deployed globally across the digital ecosystem without a unified, standardized security protocol. This compromised device acts as an unprotected bridge, instantly transmitting malicious connections to infect dozens of neighboring nodes. The attacker groups these hijacked devices into a botnet. Thousands of endpoints pool their computing power to fire an overwhelming wave of traffic directly at a single target server. Attackers use these IoT botnets to execute distributed denial of service, or DDoS attacks, forcing enterprise networks offline by flooding them with junk requests. The convenience of deploying cheap, hyper-connected hardware scales an organization's vulnerability footprint far beyond the reach of standard internal security controls. With the architecture now spanning across cloud servers and physical IoT devices, attackers adapt how they navigate the network. This is an advanced persistent threat, or APT. It slowly and deliberately weaves through multiple layers of network defenses to avoid automated alarms. It bypasses basic controls, embeds itself directly into a critical internal database, and goes dormant, establishing a permanent, undetected foothold. Modern ransomware targets critical infrastructure, encrypting data to paralyze essential services. On command, the dormant threat deploys its payload. It rapidly encrypts the host database, instantly locking the organization out of its own operational data. In real-world applications, this exact sequence cripples healthcare scheduling systems and forces municipal government networks to shut down entirely. Modern adversaries persistently occupy the internal architecture to execute catastrophic operational disruption. To manage the sheer volume of these threats, the industry relies on artificial intelligence, creating a symmetric accelerator in the cybersecurity arms race. On the left, AI's defensive capability automates threat detection by rapidly scanning massive streams of network traffic, instantly flagging anomalies in green. Simultaneously, attackers weaponize this technology. On the right, an automated offensive system generates massive red attack vectors, iterating continuously to find a flaw. Offensively, machine learning algorithms synthesize massive datasets to generate hyper-realistic deepfake audio and video, allowing attackers to commit highly sophisticated fraud. Automated phishing campaigns also use AI to dynamically adjust their malicious emails, bypassing traditional spam filters and manipulating human verification protocols. This creates a continuous conflict, executed entirely at machine speed, with systems attacking and patching themselves without human intervention. Artificial intelligence removes the human speed limit from cyber warfare, forcing defensive architecture into an infinitely escalating loop of automation. When technical architectures fail under these pressures, the resulting damage extends to severe human consequences. The massive collection of personal information across cloud networks, IoT sensors, and social media creates immense data privacy vulnerabilities for the end user. The Facebook and Cambridge Analytica scandal serves as a primary case study, where the personal data of millions of users was harvested through a third-party application without informed consent. That misuse of user data proved that system breaches carry significant societal impacts, extending far beyond financial loss. Governments globally responded to these systemic failures by implementing strict data protection laws. These cybercrime regulations penalize negligence, using the threat of heavy fines to force organizations into handling massive data repositories responsibly. We are now establishing formal ethical frameworks to govern how technology is deployed, specifically restricting corporate surveillance and unnecessary data collection. Incidents like this have made legal compliance a structural requirement, effectively turning regulatory oversight into a core component of modern system architecture. For the UUM computer science students stepping into roles as software engineers and IT professionals, your responsibilities are clear. In modern software development, security and data protection are integral requirements, rather than patches applied at the end of a project. You must adopt a proactive approach to threat mitigation. You must engineer strong defense mechanisms, access controls, and encryption directly into the initial system design phase. Your future career relies on your ability to balance the demand for rapid technological innovation with the absolute necessity of privacy protection. The final test for an IT professional is not merely building interconnected systems, it is continuously adapting your strategies to secure the risks of a rapidly evolving digital future.